All right, we got a lot of stuff to go on this one. We're going to be talking about the inverses of the trigonometric functions. And we want to understand the notation, how to use the notation. We want to know about domains and ranges of these inverses in order to come up with inverses that are actually functions. And then we need to know how to use all the right notation. And to do all of this in both degrees and in radians now that we know about radians. So a little reminder of what the trig functions do. Okay, all of them work on an angle, whether it's measured in degrees or radians, doesn't really matter. But the sine function, for example, will take that angle and it will change it into a specific ratio from the triangle. Okay. And I can replace that sine with a cosine or with a tangent. All of the trig functions change angles into ratios. It's important to remember because what we're looking for when we do an inverse, and we've talked about inverses before, we know that involves coming back this direction, and our notation for that is going to be sine, it's a little -1 up there. Sometimes you will see it written arc sine. That's a little bit older notation, but the inverse using the -1 power, we've seen that used for inverse before, and we want to remember that that doesn't mean 1 over sine. 1 over sine is a completely different thing. But this function going back the other way is going to change ratios back into angles. And so things that you have done before, we did this in the very first lesson, a reminder about how to find missing sides and angles in a triangle. So if this is in a right triangle and we had some angle in here, we might look at this where it says that the sine of the angle is the square root of 2 over 2, and we remember that sine is opposite over hypotenuse. So any way that we label this triangle on the opposite and hypotenuse, that when we do a ratio of those two sides, we end up with square root of 2 over 2, that will be true for this triangle. So if I made this I could even do this. I could do the opposite as square root of 2 over 2, and the hypotenuse as 1. And then I maybe recognize that if I want to know what this angle is, what I would type in my calculator, if I was using a calculator to do this, is sine inverse, which is an inverse or a second button on your calculator, of the square root of 2 over 2. And I would get a decimal number either way. I'd get a really tiny decimal number if I was in radians. It would be fairly small. If I was in degrees, I will get a nice clean number for this that I would recognize. This is one of the side lengths in a 45, 45, 90. So this is 45 degrees. Or if I reference my unit circle, that's the same thing as pi over 4 radians. And that's how that works in a right triangle. But when we take this to the angle of rotation, and if you remember on the unit circle, every point that's on the unit circle is a cosine theta comma sine theta pair. And so the sines are the y values. And if I look for a y value of the square root of 2 over 2, which is like 0.707, so maybe that's around in here somewhere, and the angle of rotation that takes me to that point, this is the y value again of root 2 over 2. You draw that line across there in another form. And so that's where I get my pi over 4 radian angle. That's being formed there as an angle of rotation because I know this point is at root 2 over 2 comma root 2 over 2. Okay. And seeing the root 2 in there made me suspicious that this might be a special right triangle thing. But that's not the only place on the circle where the y value is the square root of 2 over 2. It also is back here where this is at negative root 2 over 2, comma, root 2 over 2. And that is back over this direction. That's pi over 4 is my reference angle on this side. And so that's pi over 4 short of pi, which is 3/4 of pi. So over here, I would say that my theta from the unit circle is pi over 4, or it could be 3 pi over 4. As we'll see in a second, that's just the angles that it might give me that I might need to find on the first time around. Now, that's also 45 degrees and 135 degrees if I was in degrees. For the same reasons. Now, let's take that a little bit farther. We'll get away from the angles that we know from the special right triangles and talk about the coterminal angles as well. So, if I were talking about the cosine of an angle being negative 0.25, that is a negative on there. This didn't show up very bright on there. But the cosine of the angle of negative 0.25, cosine is x values. This is negative 1/2, like right there, so this is about negative 1/4 in there somewhere. And so that takes me to a point up here somewhere, a little bit angle of rotation coming around there of a little bit more than 90 degrees. And I will use my calculator. I'll do theta equals inverse cosine, or the arc cosine of negative 0.25. And the calculator in radian mode here tells me that that is 1.8235 approximately. If I were to throw it into degree mode real quick, just to verify where that is, it says it's about 104.5 degrees. And I agree with that there, and that's what the calculator is going to tell me, because the calculator can only tell me that. But I have another point down here where the x value is negative 0.25. And what I need to find that, okay, well, I can think of it as going the opposite direction around the circle to that. So I could go this way instead of this way and say it's the negative of that. So, and we want to include this, negative 1.8235 radians, or negative 104.5 degrees. If I wanted that to be positive, then I would have to add a full circle on there. If I full circle in radians is 2 pi, so if I take that answer and I added, or let's see, what's the opposite of that answer, plus 2 pi, it would give me 4.4597. Okay. And I could keep doing that. Okay, I could continue to add 2 pi to either one of those angles, because I have all of those coterminal ones. As this angle of rotation continues to turn, there will be an infinite number of times it will come by that point, and an infinite number of times that it will come by that point. So the answers really that I'm looking for here, from the green one, I would write this is 1.8235 plus 2 pi times n, where n is an integer that represents the number of full rotations around the circle that I want to do. Okay? Or I have the answer here for where the blue one is, which is a 4.45. I can actually write that. 4.4597 plus 2 pi n. Now, n is an integer, so it could be a negative number, and if I want to spin clockwise around the circle and get to some of those negative radian angles, I could do that as well. So this is actually the complete answer for cosine theta equals negative 0.25. Any one of these will get that for me. Okay, so let's do one with tangent. Tangent, if you remember, is about slope. Okay, so on a slope of a line of about a half, so I know up one over one there, a half is maybe like that as a slope. And so I can see that that also occurs in two places on my circle that I'm looking for. One in the first quadrant and one in the third quadrant. And so in my calculator, if I do theta equals the inverse tangent of 0.5, second tan, 5, I get 0.4636. That's the radian measure of that angle. And I can see that the other one is going to be, well, it's exactly halfway around the circle from it. So halfway around the circle is pi. So if I added pi onto this, in fact, for tangent, I can say that my angle that you're looking for is 0.4636 plus pi times n, because it's every half a circle from there. Now, in degrees, if I wanted to write that in degrees, I'll do that in blue here. So let me change my calculator back into degrees. And this is about 26.6 degrees plus, not pi, because this is degrees. Halfway around a circle in degrees is 180. And so I can go backward or forward around the circle any number of times, halfway around the circle in every step, and I will find another angle that when I take the tangent of it, I get 0.5. All right, so the inverse trig functions and your calculator. If we think about, I'm going to just kind of reference this unit circle here. In fact, I'm going to make another copy of it. And I thought I made another copy of it. I'll try that again. So, if sines are x values, or y values, sorry, sines are y values. So if I want to cover all the possible y values, I've got to get y values from -1 to 1. And since sine, if I start over here with my angles like this, I will go from, and I'm rotating around this direction, I'm going to go from y values of 0 to 1, and then 1 back down to 0, and that's going to fail my horizontal line test. And so the horizontal line test tells me that that won't be a function, the inverse won't be a function. So what I have to do, the easiest way to get to this, is if I also include the angles going back down this direction. Okay, so from -pi/2 to pi/2, if that's the only angles that I look at, then that tells me I'm looking at this part of the circle, and that part of the circle will pass the horizontal line test. Okay, so its inverse will be a function. And that tells me if that's the domain that I have to restrict the sine to. So if I want sine to have an inverse that is a function, I have to restrict it to negative pi over 2 to pi over 2. And those can be closed brackets. Okay? If this is the domain of the function, then it becomes the range of the inverse, which means that inverse sine can only give me numbers between negative pi over 2 and pi over 2. So it's never going to be able to tell me all of those angles. Okay? It also, since the range of the sine goes from negative 1 to 1, it tells me that the domain of the inverse sine, the domain of the inverse sine is going to be from negative 1 to 1. I can't put any numbers bigger than 1 or smaller than negative 1 into the sine. Okay? If I'm talking about cosine, cosine is the x values, and so for my x values, I can get, as I go from here to here, I get all of my x values from 1 to negative 1 as I rotate from 0 to pi. So this one has a domain restriction of 0 to pi. If I want to make the inverse a function, so the inverse cosine function also has a domain of negative 1 to 1, but it can only give me answers between 0 and pi. I'll never get a negative number out of an inverse cosine. And if I were trying to look at this for tangent, tangent is my slope. So I want to cover all of my possible slopes. And if I start over here in the standard position and keep going this direction, oops, that didn't even go through the origin. That's no good there. They are also going to use for the tangent function, even though we can, as we go through here, we're going to get positive slopes and then negative slopes. If we go from 0 to pi, we would also get them if we went from negative pi to pi over 2, and they tend to use that. Negative pi over 2 to pi over 2 as the domain, which means my inverse tangent, the domain of the inverse tangent, my slopes of lines can be anything. Okay? So the domain of the inverse tangent is all real numbers. Which means the range of the tangent was all real numbers. And the range, since this negative pi over 2 to pi over 2 was the domain of the tangent, it will be the range of the inverse tangent. All right, let's do some examples. I know this video is getting long. I said we had a lot of stuff to get in here. So find all the possible values of inverse cosine of square root of 3 over 2 in radians and in degrees. Okay? Well, inverse cosine, so I'm talking about x values here that would be square root of 3 over 2, and I recognize those numbers. So I want an x value that's out here at square root of 3 over 2, and I recognize that as being my 30, 60, 90 triangle, and this is the 30-degree angle over the pi over 6. So the very first one would be that theta is equal to pi over 6, but there's another x value that would have, or another angle that would have that same x value, and it's negative pi over 6. So it's pi over 6 plus 2 pi n, and negative pi over 6 plus 2 pi n. That's all of the solutions in radians. In degrees, it is theta equals 30 plus 360 n degrees, or negative 30 plus 360 n degrees. It's an infinite number of them. Now, example 2, evaluate inverse tangent with a capital T. When it says with a capital T, it's talking about only the number that the calculator would give you. Okay, so this is an easier one to do. We don't have to put the plus 2 pi plus 360 onto this one at all. Now let's take a look at that square root of 3. Sounds suspicious. I know that one. That is the steeper line that shows up here in my 30, 60, 90 triangle. So that's for the 60-degree angle would be pi over 3, but this wants it going the other direction with the negative slope. So it looks like it is then going to be my negative pi over 3. So the inverse tangent of negative root 3 with a capital T is just negative pi over 3. And I'm not going to change that into a positive number because this is the number that the calculator would give me, okay, if I did that. All right. And one final type of problem here, since it gives me an infinite number of answers, I don't always want an infinite number of answers, so it may give me a specific place in which to find that answer. So, if this is specified in degrees here to begin with, so I'm going to change my calculator, make sure that it is in degree mode. And the first step is going to be to say theta, then I want to see what the calculator gives me for the inverse sine of negative 0.56. So second sine, negative 0.56. Tells me it's about negative 34 degrees. Okay. But negative 34 is not between 90 and 270. So I need to start adding things on here. Let me draw the picture of the unit circle again and see exactly where I am. The sines are y values of negative 0.56. That's down here somewhere. And I just found this one, but I want to be somewhere between 90 and 270, so I want to be over here somewhere. Adding 360 is not going to do that. I'm going to have to find the other one that got me down here. Okay. So this reference angle is 34 degrees. I'm looking for this one over here. So it's going to be 34 degrees down this way from 180. So 180 and 34 is 214 degrees. So using all of that information, the angle that I'm looking for is a 214 degree angle. All right, I believe I covered what I was hoping to cover in there. I'm sorry for how long it was, but there was a lot of information that needed to get out to you.